So the very first kind of stress that we're going to look at is a concentration stress. Concentration stresses are the easiest LeChateliers Principle problems to work. So as we look at our standard mass action equation right here, in which I have A and B going to make C and D, you need to understand that there are basically four kinds of things that can happen. I can either add A or B to the system, or I can add C or D to the system, or I can remove A or B from the system, or I can remove C or D from the system. So let's just think about LeChateliers Principle and what that means then with respect to what direction we shift. If I add A or B to the system says, I don't want more A or B. I have to shift to get away from having more A or B. So which way would you shift to get away from having A or B? Well, obviously, since A and B are on the left side, if I add A and B, you shift right to reduce A and B. Notice as a consequence, I make more C and D. Suppose I add C and D. Well, what I need to do is fight that. I need to move away from having C or D, and the only way I can do that is to shift to the left to reduce the amount of C and D, and that consequently increases the amount of A and B. Suppose I remove A and B. The reaction says I don't want to remove A and B, so I need to add A and B internally. The only way I can do it is by shifting to the left, so the C and D goes down and the A and B can come up. And finally, I remove C and D. The reaction says I don't want to remove C and D. I'm going to add C and D by shifting to the right to fight that stress. I increase the amount of C and D, and I reduce the amount of A and B. So concentration stresses are really a pretty simple sort of thing. Whatever happens, adding or removing, you simply fight that by moving in the direction to remove and add as a consequence. And then you look at the result. So let's go ahead and take a look at this particular example right here with respect to concentration changes. I've got hydrogen and nitrogen making ammonia, and they're at equilibrium. I'm going to stress it. Maybe I'm going to stress it by adding a bunch of hydrogen and nitrogen. If I add hydrogen and nitrogen to the system externally, then the system says, I don't like that. I'm going to fight that stress. The only way I can fight it is by reducing it by shifting to the right. I end up making more ammonia. I end up making less hydrogen and nitrogen. Conversely, suppose I've got ammonia in equilibrium with hydrogen and nitrogen. Now I suck the stuff away. I'm pulling the ammonia out. This is actually what people do when they take the product of a reaction like ammonia and they want to take it off to make fertilizer. If they pull it away to go make fertilizer, then the system says, hey, you've taken my ammonia away. I need to make more ammonia. And this prompts the system to shift to the right to make more ammonia. And so this is a nice way in chemical reactions for us to be able to produce product and to drive a reaction thermodynamically by removing the product from the system so the system is constantly shifting to the right to make more of it. I now want to talk about the effects of pressure changes on systems. Now actually, as I tell you about the stresses coming from pressure, you should appreciate the pressure and concentration changes are effectively the same sort of thing, because we saw that the relationship between Kp and Kc is one in which concentration and pressure are actually the same thing related through RT to the delta N. So in the same way I could talk about concentration changes and the impact they have, pressure changes are really no different. So here's an example down here. I've got water reacting to make hydrogen and oxygen. I could write this as a problem in which I talked about the amount of water going down or up, or hydrogen and oxygen going down or up as a concentration change, but instead I'm going to talk about it in terms of changes in pressure. So watch this. I'm going to decide, for example, that I'm going to increase the pressure of this system. What is the system's response? It says, you've increased the pressure externally. I don't like that. I want to shift away from that pressure. Well, if you look at this chemical system right here and ask, in which direction should I shift now that you've increased the pressure and I want it to be smaller? Well, you look at delta N here. You see that if you've got 3 moles of gas on the right and 2 moles of gas on the left, then you need to shift to the left to reduce the pressure. Or suppose I decide that I am going to decrease the pressure. The system says, wait a second, I don't like it when you decrease the pressure. I'm going to have to shift to fight that, to increase the pressure. So the system looks and says, well, what way can I shift to increase the pressure? The answer is I shift to the right. I go from 2 moles to 3 moles by shifting to the right. So generally speaking, in this particular case here, if I want to externally decrease the pressure, then I shift to the right to increase, and if I externally increase the pressure, then I shift to the left to decrease. Of course, at this point, that good old trick that we show you, in which we show you a chemical reaction in which delta N of the gas is equal to 0, and ask, well, how is this system impacted? You'll notice that if I have no gas molecules, then the pressure change is going to have no substantial effect on the system. So I can increase the pressure on this system here where I have solids becoming liquids, and there's no effect. I can decrease the pressure, and because I have only solids and liquids, there's no effect. I can even choose a system for which everything's a gas. And you'll notice, because I have 3 moles of gas on the left and 3 moles of gas on the right, the delta N of the gas is equal to 0. And this means then that if I stress the system by increasing the pressure, or if I stress the system by decreasing the pressure, the system can do nothing to fight it either way, so there's no change, no shift to the left or to the right. So general rule of thumb, when I have pressure stresses on systems, you have to look to see whether or not there's a change in the number of moles of gas possible. If there is, then you can in fact have the reaction shift either to the left or to the right to either increase or decrease the number of moles of gas to fight the stress that's applied externally.